I wanted to talk a little bit today about different ongoing research directions that we have in our section at DTU, including Shobit, who is here in the back, related to incentivizes prosumers in energy communities to provide flexibility and how to design energy markets for those communities that are fair, efficient, and secure. So this talk is a little bit organized around different papers and works that are related to each other's. And I also have some backup slides in case we go really fast and you want to hear more. So first of all, we have to define what an energy community is. And we're lucky in Europe, actually, the EU has legislated and defined in the Clear Energy Package what an energy community is. And they've set pretty ambitious targets, actually, to have one energy community per municipality of a population of more than 10,000 habitants. So typically Graz should have an energy community. Does Graz have an energy community? Anybody knows? I haven't done my research. Yeah. Mm-hmm. Copenhagen and a few. Mm-hmm. Yeah. Mm-hmm. Okay. Yeah. Mm-hmm. Yes, Denmark is also really big on energy communities, both in big cities, but also remote areas. So currently, there are over 2,000 active energy communities already in Europe, and 1.5 million citizens. I prepared that a few months ago, so this might be more by now. But my point is that energy communities are not science fiction anymore. It's not something that might happen. It is happening. So this research is very much important at this time where we're increasing the number of energy communities drastically. So how does the EU define an energy community? So an energy community, one important thing is that it's a type of entity that is based on voluntary participation. So nobody has to join an energy community, and participation is open. Everybody can join. And it is controlled and owned by its members. So that's the difference with an aggregator that's operating for profit compared to an energy community. And the primary purpose of the members of that energy community is not purely economic. It's not only to make profit by participating in electricity markets. It can be environmental, economic, or provide social benefits for the local community. And that is an important distinction, which also makes it both more attractive for consumers to join an energy community, but also more challenging to design energy markets that are fitted to these consumers that have not purely economic goals when joining these energy communities. So that's why I think it's actually a really fun problem to look at energy communities. This is where you can actually try actually fun market designs compared to redesigning the day-ahead electricity market. So I really like this research topic, and I hope for those who are not yet working in this area that maybe this inspires you to consider looking into energy communities. So what is the role of energy communities in the power system? Of course, it has many potential benefits. Otherwise, we wouldn't be looking at them. They can harness the consumer's flexibility by allowing them to self-organize and join forces and facilitate their participation in energy markets that already exist. They can also help consumers advance energy efficiency and social acceptance of renewable energy sources. This is a big challenge also in Denmark, where there's sometimes resistance to installing wind turbines. So energy communities that co-own those wind turbines also help increasing their social acceptance. There is also benefits for the grid, because by allowing consumers to be more active, these communities can provide grid services, so specifically to the distribution system, but also in some cases, if they're big enough, to the transmission system. And finally, one last potential benefit is that those energy communities don't address only technical and economic challenges, but they can also provide some social and environmental benefits to the local communities and the prosumers within them. But there are still some pretty big remaining challenges, of course, to help develop those energy communities, but also to do it in the right way so that they are beneficial for everybody. First challenge is the regulatory and market frameworks that currently exist. Often they limit what energy communities can do. They haven't been created for energy communities and for small prosumers being active. So they don't usually provide adequate incentives for those energy communities. That's one challenge. Another challenge is that there's a lot of algorithms, market mechanisms, control algorithms that are developed in power systems to control flexible assets. A lot of them are not particularly suited for prosumers that might have complex preferences, sometimes not just economic, and also unknown preferences, because those preferences for consumers are typically very sensitive and nobody is willing to share their full preference as a consumer. This leads also to privacy leakage and cybersecurity concerns. When prosumers participate in those markets, they want to be sure that their sensitive information is not going to be leaked to third parties that they do not trust. And finally, and I'm not going to talk that much about this, but Shobit, I think, is going to talk about this, is that a lot of algorithms that try to optimize the participation of prosumers in energy communities require quite a big communication burden for those consumers. And of course, we have smart meters and smart homes and smart appliances, but prosumers still need to make decisions when they participate in those markets, and nobody has unlimited time to look at their apps and optimize their energy consumption. So those mechanisms, when we design them, we have to take that into account if we want prosumers to actually use them and use them optimally. So those are all big challenges, and I'm going to try to address some of these in the proposed approaches. So I wanted to highlight three potential research directions and then show a little bit what we're doing in those areas. But of course, none of them is fully answered. So the first research direction is can we actually quantify the benefits of energy communities? Do we know that they are beneficial for the system? And are they viable economically? Is there a business model for people to participate in them? If we can first ascertain this, then we can go to the following research questions. Otherwise, there is no need to look into them. So if we know they're beneficial, then we want to harness these benefits. So we want to design efficient local energy markets, even when we don't know the prosumers' preferences, or they have limited communication, that will harness this flexibility. And the third research direction is, okay, if we manage to do this, we have this nice mechanism that harnesses the flexibility of our prosumers. It gives good incentives for them to participate, but they might have some concerns about privacy or cybersecurity, which might not incentivize them to participate in those markets. So how can we alleviate that? So this third research direction, I'm including as future research, and I have some backup slides if you have questions about it. But I'm going to focus on those first 2 points. So first of all, what are the actual benefits of having energy communities? Can we quantify this? So I have a motivating example of an energy community that provides flexibility services to the DSO. We're trying in this research, you can see the reference down there, that's a paper published by a student, which is, what was I going to say? Yeah, how can these energy communities provide grid services? So we're looking at a very specific case, and we're trying to quantify how much they can help the DSO and whether or not it's beneficial for them to do that. So why do we need to do that? You have the example here of a local area in Denmark. Actually, this is the area where our head of section, Jalal, lives. You can see his head here. Don't worry, I didn't put him on the actual house, but this is where he lives, and this is the transformer that serves his house. And here you can see the data of the transformer loading in this exact area in 2024. So you can see that in certain hours, it is approaching the maximum transformer capacity. So why is it? Because this is a very nice area, and more and more people are having EVs in this area. So of course, this is causing some issues for the local grid. So in this context, Radius came to DTU and asked us, how can we harness the flexibility of consumers and incentivize them to help us reduce this transformer loading? We don't want to invest in a new transformer, but we would like to harness the flexibility of consumers. So what they want to know first is there a potential for energy communities to provide those services? Are they capable of doing that? And how much could we harness from them? Just knowing that would help us know how much we can delay investment, for example. And is it beneficial for them? What kind of incentives should I give them to make it worth their while to give me those services? So the main objective that we had was to provide a framework in which we could quantify the best case of the flexibility that is available in an energy community and the benefits that they can provide to the DSO. So, of course, when we talk about flexibility, there's a lot of types of flexibility, a lot of services. Here, we're looking at a specific case. We're looking at it because this is also what the DSO was interested in this case. So we're looking at an energy community that would provide capacity limitation services. Here you can see a group of houses. Let's assume this is where Jalal lives, and this is the transformer that is sometimes overloaded. You can see in some hours, the load might exceed the capacity in this line. So what does the distribution grid want to do? They want to enter with this community some sort of contract asking them to reduce the capacity and the strain they put in the network in this area, right? So they want to incentivize people in this area to form a community and impose some capacity limitation in this area. In exchange, of course, they are going to reward them for doing this, right? So you can see the benefit is that the community would reshape their loads to help the distribution system operator. In exchange, how is the distribution system operator going to incentivize them? So we looked at a framework where after the day-ahead market has been cleared, the DSO tries to forecast congestion. Is there going to be overloading in this line or in the rest of the network? What quantity of services do I need from these energy communities? Once they've done that, they are going to compute a capacity limitation that they're going to put on this line and the grid tariff discounts that they're going to offer the members of this community. This means that inside their community, they're not going to pay grid tariffs, which are pretty high and they account for a big part of your electricity bill. So any flow that stays within the community, if they exchange between each other, they will not be charged for this. Any flows that goes outside, if it is below a certain amount, that's fine. If it goes above, there will be some penalties and increased grid tariff. So through this mechanism, they send that to the community manager, and now the community manager has to think, okay, how do I make sure that people together reach this objective? So the community manager is going to set prices for each hour, compute the optimal prices for the energy community, for each member, so that when the consumers observe those prices and optimize their loads, and when they decide when they want to charge their EV or run their dishwasher, they will make a decision that's coordinated and that will respect these constraints and help the DSO. So of course, in this case, the prosumer always has full control of their assets. They only observe a price and decide how to respond. So the way these prices are set is important. So what we're trying to see is by setting prices, how much flexibility, how much can we change the behavior of the prosumers to create benefits for the system operator. So this process is the day before operation. This is not a real-time mechanism. Just want to emphasize this. So what do we mean by dynamic pricing if this is not a real-time mechanism? Well, if you looked at static prices, through the day, you always have the same prices at each hour. And for all prosumers, they have no incentive to move their load. You could have time dynamic prices where you vary those prices through hours to harness intertemporal flexibility. And you could also have time and space dynamic pricing, which now are differentiated depending on where you are located in the grid. So you could argue that maybe this is not fair, but we're going to talk about this. So each prosumer in the community, depending on where they're located, might observe different prices. So this problem that the community manager is facing, which is how do I set optimal prices, is a Stackelberg game. So we took a game theoretic approach. We said this problem is a game between two players, the community manager and the prosumers. The community manager plays first. They're setting the prices, they're optimizing the prices, and then they're observing the response of the consumers. The consumers, when they see the prices, decide how to schedule their load optimally. So in this game, the community manager, who sets the prices first, has to anticipate how the prosumers are going to respond to those prices. How can we do this? Well, we can model this problem as a bi-level optimization problem. Basically, in the community manager optimization problem, in which they set the optimal prices, we are going to embed as constraints the optimal response of each prosumer in this community. So this optimization problem, typically, the community manager would want to maximize the social welfare in the energy community, and they're subject to internal network constraints, so within the community, and also the capacity limitation set by the DSO. In addition, because we want to set those prices in a way that benefits the community as well, you have to think this community manager is co-owned by all the community members. So we also want good properties of those prices. So first of all, we want them to be individually rational. This means that we want to enforce that no community member would lose by joining this community. Second, we want budget balance for the community. Of course, we don't want the community manager to be in deficit by setting very low prices. And third, we're also including fairness considerations in this problem. Of course, there's different notions of fairness. I'm not going to go too much in detail, but the community members can agree to enforce some types of constraints on fairness and how the prices are distributed across prosumers. In the extreme case, they could agree that everybody has the same prices or that everybody has the same cost overall. Or they could have more advanced notions of fairness as well. And finally, we have to model also the prosumer's problem. So the prosumer's problem is to find their load schedule for 24 hours tomorrow that maximizes their own surplus that they derive from this energy. So that means minimizing the cost of procuring it and maximizing the utility they get from it. And they're subject to some operational constraints, maybe on when they want to use their EV, when they want to cook, how much capacity they have in their battery, etc. But those constraints are different for each prosumer. So if we formulate this optimization problem, we can recast that as a single level optimization problem, do some fancy reformulation, and we can solve this problem from the perspective of the community manager. Of course, if we know all the prosumer's load scheduling problems. So what kind of prices can we set, and what would we achieve by using this approach? So first of all, we made a small simulation, a small example of an energy community. You can see that this is the residual load of this energy community without any flexibility mechanism. This is what these consumers would consume if they were left alone, right? Based on just grid prices and flat tariffs. So this is it. And you can see the capacity limitation that the DSO would want to impose on that day. And of course, during the peak in the evening, this community is exceeding this capacity, right? So what if the DSO was sending this grid discount and these capacity limitations to each individual prosumer and telling them, can you help me individually reduce your load in these hours? I'll give you some discounts on your grid tariff. Well, if they sent the same grid discounts to each community member individually, what would happen is that uncoordinated response, you would actually observe a peak in a different hour. Everybody would have a very similar reaction. So you risk actually having this rebound effect where energy is cheap, then everybody consumes. So you have an even worse case for the grid operator. Of course, that doesn't happen all the time, but in the worst case, this is what we observed in the uncoordinated demand response. So what is the benefit now of the energy community and having a community manager that coordinates the response of the consumers? So by setting dynamic prices, this is the response of the consumers that we managed to observe. So what we see here is that we successfully adhere to the capacity limits that is set by the DSO. So this mechanism helps us achieve the goal of helping the distribution system operator. That's great. But does it benefit the community? Right? So we looked at different cases, depending on what kind of discount the community manager, the distribution system operator is willing to offer. So here, along the y-axis, the discount rate that the DSO is offering to the community increases. And here, along this axis, we changed the capacity limitation variation between hours. So for a very low value, this means the DSO sets the same capacity limitation through the whole day for each hour. For a very high variation, we observe a lot more volatility in between hours in the capacity limitation in that line, right? And this we made proportional to how much congestion there is in the grid and how high the day-ahead prices were in this area. So this means that the DSO is imposing actually much stronger constraints in the hours where everybody wants to consume. Of course, this is more beneficial for the DSO, but what we observe is that if they increase this variability, then the cost for the community, or is that a cost that I'm representing? Yeah, the cost of procuring that energy for the community increases. So it becomes less and less beneficial for the community as a whole to participate in this mechanism. So there is here a trade-off that the DSO has to find, which is how much flexibility they can extract from this community versus how to still set a mechanism in which the community members will benefit, in which they will want to participate and they will make profit. In all these cases, I want to point out that the community still makes profits by using this mechanism compared to not providing this flexibility. So even the highest cost is better than not participating for the community. Now, we also want to look a bit more in detail inside the community. Okay, there is potential economic benefit for the community as a whole, but what about for each consumer? Are they better off individually than if they were not participating? So we look here at the benefits compared to a benchmark case. We have the one where we have no fairness redistribution. We look at one mechanism where we have proportional fairness and one where we have equal sharing of the benefits. So what are of the prices, at least. So what we see is that if you look at these green, highlighted in green, those community members, actually for them, the fairness promotion successfully captures how much they contribute to the community and successfully redistributes the profits among them. Of course, you have different behavior depending on equal versus proportional sharing, where proportional sharing would most likely be advantageous for people if you have a bigger load overall versus if you have a small load. So that depends also which one is most beneficial, depends on the makeup of the community, but again, this is something that community members have to agree on, which notion of fairness is most beneficial. So just to conclude on the takeaways of this work, right? What we just showed is that, yes, an energy community can provide services that benefit the grid, and also that there is socio-economic benefit for this community in joining forces and providing those services and helping the grid. So now that we know that, however, this is not a practical framework to coordinate these consumers, because right now I just assumed that I knew exactly how they would respond to my price settings. So this is a very optimistic case. Instead, in research 2, we are focusing now, how can I actually design a local market that would help me coordinate those consumers without assuming that I know everything about them. So why do we need to learn the prosumer's preferences? Well, we saw that in the approach that we had earlier, we assumed that we knew exactly which assets prosumers had, what was their objective, how they would respond. Then we could set optimal prices. But if we did not have this information, we could not formulate even the optimization problem that we had. So what we have in a more realistic way is that we have uncertain knowledge of the prosumer's assets. We don't know who has a battery, how big it is. And we can have maybe some prior information or some guesses about who has different assets or how they would respond to different prices. So we're trying to represent this uncertainty and also update it and learn more and more about the prosumer's behavior as we continue optimizing their load scheduling. So we are still looking at the case of a dynamic pricing mechanism where the community manager is setting prices, and we're trying to find a way for this mechanism to incentivize the consumers to act flexibly, but without truly knowing their preferences and the assets they own. So to do that, we want to design a dynamic pricing mechanism that learns how to set optimal prices. What that means is that we want to learn while optimizing, right? We want to learn the optimal prices. This means we want to learn the preferences of the consumers while we are optimizing the prices to have the best possible response from them. So each day, we're not learning from a very large historical set and approximating their preferences. We are every day setting some prices, observing their preference, their response, and while we gather this information, then tomorrow we can make better decisions and send better prices to those consumers. So what exactly do we mean by learning and by prosumer preferences? So just to clarify, what are prosumer preferences? Well, if you have a smart home with a lot of different appliances that are flexible, your preferences, they can reflect what type of assets you have, but also how you like to use them. So for example, at what time are prosumers at home and able to shift load? What flexible assets do they have? What temperature do they like to keep their home at? How do they have an electric vehicle? When do they drive? All of these questions that we do not have an answer for, but that characterize how consumers behave and how they respond to prices. So, now, to solve this problem, we need to find a framework to model those preferences of all the consumers. So what we're using is we consider that a prosumer's household, their aggregate demand profile can be disaggregated into multiple elements that we call signatures. Each signature can represent a different asset, a different way to use that asset. So there can be many, many signatures that make up a smart home. So the signature is going to represent the power scheduled for an asset within the smart home using an optimization problem. So each signature, of course, does not contribute to the total consumption of the prosumer in the same way. So we assign a weight to each one of these signatures, and this weight represents how prominent this signature is in the household's aggregated demand profile. This means we could generate a lot of signatures. Some of them, for some consumers, might have a weight that is 0, right? If I have a signature for EV, for example, then if a consumer does not have an EV, the weight for this should be 0. But while we're assuming we know the pattern of these signatures, what we don't know is the weights of the signature for each one of the prosumers. So what we are trying to learn is what is the weight of the signatures for each prosumer. We are assuming here that each prosumer is perfectly rational and they're always trying to optimize their consumption to minimize the cost. That is the assumption we're making, so that they are not acting randomly, but optimally. So, what we're going to use, because we want to optimize the prices while we are learning those weights, we are going to use an online learning or bandit framework. So the typical bandit framework, we have initial knowledge about those prosumers. It could be very vague. It could just be, 50% yes, 50% no. We want to first we set dynamic prices based on this initial knowledge. Then we observe their response. Based on that, we update our knowledge. And then, again, we set dynamic prices with this updated knowledge. Now, we're using a specific version of this, which is Thomson sampling. What we do assume is, yes, we have initial knowledge of the prosumers, and we represent that as distribution, a prior distribution of the weights of each prosumer and each signature. Since we have a distribution, we don't have one value for these weights, we need to sample a value from this prior distribution. We're going to use this sampled value to set optimal prices. Once we've set optimal prices, of course, we observe the response of the prosumers, which means we can update the distributions. We can calculate the posterior distribution using Bayes' law. And now we're back to optimizing again. So we have an updated distribution. We're going to sample from this distribution and set prices again. The benefit of this approach is that you are endogenously finding a trade-off between exploration and exploitation. As you have a very wide prior distribution, your samples will be all over the place, right? So you will try different approaches. But as your posterior knowledge becomes more and more accurate, then your samples will be more and more targeted towards the area where you think the true weights of the consumers lie. So can see in this approach, we have a distribution of the true value. After a few iterations, this distribution converges towards the true value, at least that's the hope. And we start now only sampling for the true distribution and therefore setting prices that are more and more optimal as we learn. Yeah, so the big difference is this sampling approach in the Thomson sampling compared to other online learning approaches. So now that we have this approach, we need to reformulate the bi-level price setting problem when we want to optimize the prices. Initially, we had one lower level problem that represented the aggregate response of each prosumer. Since we now have signatures, we are going to decompose this to have lower level problems that represent the response for each signature and each prosumer. So we are introducing more lower level problems that we disaggregated. And then we add a constraint that represents what is the aggregated response weighted for each prosumer. So what we will observe, what does this do, right? So first of all, what we want to observe is, are we able to learn compared to if we had perfect knowledge? So what is the regret of this algorithm? What we observe is that if we compare the daily community cost with our approach compared to the daily community cost if we knew everything about them, we converge toward a near zero regret. So we are able, after a few days, to make optimal decisions, set the prices optimally for the community. So we can see here, after approximately 100 days, basically we have almost zero regret. We did that, of course, over many independent runs. And you can see that in some cases it converges faster than other, and this is the range of the regret that we observe. Then the second question is, okay, we set the prices optimally, but that doesn't mean we actually know how people are truly behaving, right? And why they are behaving this way. So we looked at actually, are we learning also the true weights of the prosumers? Or are we just learning something that behaves similarly? Where we looked at the true weights in red here, this is our initial distribution, right? This is the prior distribution. So we start from this, which is very far from what is true, right? So after 5 days, you can see that some of those signatures have already converged. Basically, we're sure that this consumer, in this case, does not have this signature. Some of them have converged, some of them have not converged. After day 25, we have other signatures that start converging. Day 100, so now all our signatures have converged. So we've actually learned what assets this consumer has and how they like to use it. What we observe is that the signatures that have the highest power consumption are the ones that converge first. It makes sense, right? They are the ones that are the most prominent in their response. So I guess that's kind of intuitive. But anyway, after that, we still learn every preference of the consumers as long as we have set enough signatures that they represent the true signatures of the consumers. Now, are we also able to still provide services to the DSO? So what we see is that on day one, so initially we saw after 100 days, right, we had zero regret and we were setting optimal prices. What we observed here is that we're learning how to help the DSO actually even faster than this. On day one, we don't know anything about the prosumer, so we're setting prices all over the place. Our learned response is terrible compared to what would have been the optimal response, which is green, right? So we're not helping the DSO at all. In day 5, we are almost already there, right? We're, from the DSO perspective, our aggregated response is almost optimal and we're respecting the capacity limit. Why does that happen faster? It's because we are actually learning faster the signatures that have the highest capacity. So the ones we haven't learned, they are very small and do not make up a big part of this aggregated consumption. And then we keep looking day 25, day 100. We are following still the capacity limit set by the DSO. So this is good. So the main takeaway is that this learning algorithm that integrates bi-level optimization and Thompson sampling is able to learn the preferences while optimizing the prices to get the best possible response from the consumers. And we see that we have really nice properties for this algorithm. We achieve near zero regret, and we learn how to reliably help the distribution system operator. So just to conclude, so what we've seen in those research directions is that, yes, energy communities are beneficial for the grid. And I'm sure this is not the first time that you hear that. But in this case, we wanted a way to quantify how beneficial they were and what is the trade-off between benefiting the community, prosumers, and the grid. And we see that we can achieve both at the same time. And second, we looked at how can we design a practical setup to coordinate the response of those consumers without assuming that we know everything about them. And we see that we can actually do that and quite quickly learn how a community will behave. So conclusion is, at least from my part, I hope you agree, that energy communities can be an important piece of the puzzle to support green transition of the power grid in Denmark, but not only in Denmark, also in Europe and Austria. So future perspectives, of course, you might say there's a big problem with what you presented. You have now showed how you can learn some pretty sensitive information about the consumers in the energy community who would want to participate in a mechanism that is doing this, that needs to do that to work. So how can we balance the trade-off between needing to know about the consumers to be able to coordinate them, but also be careful and be respectful of their sensitivity to privacy. So we have some research that is ongoing on privacy preserving local energy market or aggregation of flexible loads. And yeah, if you have some questions about it, I'd be happy to talk about it.